Thank you. I'm Adam from Pinterest, SRE team. How many people have in here used Pinterest? Not that many. Okay. I mean, wow, I can't believe there's so many of you that use Pinterest. My talk is on, well, I've retitled my talk to Invisible OS and Platform Upgrades because that's really the target, is to make these invisible to the service owners and to give them a way to not have to worry about platform and OS upgrades. Introductions, this is Pinterest. Pinterest, this is everybody. Pinterest is a site where you can essentially, well, our mission is to bring everyone the inspiration to create a life that they love, and in order to fulfill that, Pinterest is a mostly link sharing and photo sharing site, but we do have some advanced features that allow you to search for things visually. A lot of people prefer to search visually versus searching with words, and this is a way for them to do that. This is me. I'm on the core SRE team at Pinterest. Mostly we care about overall uptime of the site, the internal services that we support, and we do a lot of cleaning up of tech debt and managing ownerless services. That would be like services people who left the company left behind when they left, things like that. I've been using Linux for quite a while. I've been a sysadmin since 1998, and I started doing DevOps work around 2012, that area. So what is the problem? We, or actually they, talked about that a lot before spinning up this project, and they came to the realization the problem is essentially that software goes out of date. So we have all these different things that are beneath our application, such as the OS container, runtimes, Ubuntu, Docker, Windows. We don't use that at Pinterest, so. Language runtimes, we use Python, Java, Go, and C++. And we must upgrade. That's just a fact, because the business needs to retain support on operating systems, runtimes, Python, everything that is going out of end of life. We need security bug fixes. We need access to new features. For example, there are new EC2 instances, families take advantage of more modern processors, different kinds of hardware support. For example, machine learning GPUs. We need drivers for those, and Ubuntu 14 doesn't really have very good GPU drivers. Performance, we expect a lot of the time that new operating systems and new runtimes will have better performance. Unfortunately, that's not always the case, especially with things like Spectre and Meltdown, where they had to put in some things that actually worsen performance. And then there's the new storage technologies or other storage technologies. For example, we have to go from C3 to C5 instances and take all of our instance store data and put it on EBS. That causes a slowdown. We talked about some of these issues and war stories in another presentation last year. My colleagues Ruth and Rodrigo talked about that. If you're interested, that's the link. So what do developers want? They want access to new packages and features. Like I already said, updated runtimes, GPU drivers. They want platform efficiency, which means they don't want to do any of this stuff here, because this sucks. They want to avoid supporting multiple OSs. They want to be able to upgrade cleanly. Maybe have 2 of those lines, but not 6. But we hates upgrading. That was my Gollum. It should be read in a Gollum voice. We hates upgrading. Upgrades are complex. We have hundreds of microservices across tens of thousands of hosts at Pinterest. Service owners, they don't like downtime. I've never met a service owner that's like, I hope my service goes down tonight. Migration work's not really that fun. People don't like it that much. It's not a preferred task for a lot of people. And developers, they want a consistent API and ABI for their programs and code that they're writing. And they've written tests around the old versions, so it's harder for them to upgrade because they have to do twice the work. They have to upgrade their code, and they also have to upgrade the tests. So our solution to this was an automated canary analysis system specifically targeted for these lower level components. So canary analysis, I don't know if you guys have heard the term before. It's not what's in that picture. That's a joke. But what is it? It's comparing the behavior of and performance of two different clusters, one control and one canary. Essentially, the control cluster would have the current code on it. The canary would have the new code. It has inherent risk, obviously, running things in production, running new code in production. But it's a lower risk to run newer code on a small number of systems or a small percentage of systems than to risk rolling out that bad code everywhere. And then this is just a link if anyone's interested. It talks about, it's called a risk matrix. It talks about the severity and likelihood of different events happening and how to kind of calculate whether or not, or essentially how that works. I'm just going to move on. So requirements or goals. We wanted to automate the most mundane functions of migrations. So nobody likes staring at graphs, or maybe some people do, but I don't. We want to make sure to depend on a successful integration and acceptance testing because we don't want to deploy bad code with our new runtimes. We want to automate looking at charts and comparing metrics, like I just said. And we want to normalize the process so that it can be applied to multiple different services, which run on similar systems, similar software stacks. We want to make the migrations invisible, like I said before. We don't want the service owners to have to worry about them. We want to address their reliability concerns before they happen. We want to analyze the services at the cluster level, not the host level. A host can have a problem, but that could be constrained to a certain host or a single host. If the entire cluster is having a problem, then you know something's wrong. They can be run by an operator, so a developer doesn't have to sit there and waste their time. An operator can just click a button and everything runs automatically. If something goes wrong, operator clicks rollback, and that's it. And we don't have to do this anymore, hopefully. We have the system that does everything for us. So the typical migration pattern is essentially we release a new image, or this is the old pattern, or what we're trying to get rid of. Service owner says, hey, well, the new image is released, and the image guy or the image girl sends an email saying, hey, everybody, new image is available. Nobody reads those emails, but someone eventually will notice that there's a new image. They'll update the image ID in the deploy system. An operator will say, hey, there's a new image. We need to roll it out to all our servers. He'll click that button to trigger a cluster rolling upgrade. Humans look at the charts. They cross their fingers. Did things go okay? Okay, good. Did things not go okay? Bad. Everybody roll back. I hope there's not an outage. So we can look at what the normal process is by looking at these two graphs. Anybody think that if they saw these two graphs, a control and a canary, that they would want to say, yes, let's roll this out? Raise hands. Anybody? So the left side is control, the right side is canary. So the right side would be the new code. Yeah, I wouldn't roll that out. Doesn't look good. How about this one? Anybody, who would roll this out? Looks pretty good, right? I mean, memory, CPU are pretty close, but something weird going on with I/O maybe? We don't know. But let's ask the service owners. So this is Gene. Gene is very risk averse. He doesn't like change. His service has over 7 nines of availability, but it's still running on Ubuntu 10. What do you think Gene's going to say when he sees that I/O line? No way. Let's meet on Monday and figure what's going on. So now, not only do you have a delay in your project, you have to have a meeting with Gene on Monday. And that's probably not going to be fun. This is Angus. His last job was at a Bitcoin startup. He likes to move fast and break stuff, and yells, tonight we test and prod at least once a day. I've never actually had anyone yell that, but I've seen it in commits. Angus's call, he says, let's go, ship it. Looks good to me. This is Carol. I don't know if you guys have noticed, but these are all Snapchat filters of me. Carol has 100% test coverage on all her code. She's researching statistical models to improve fault detection. And analysis is her middle name. She loves this stuff. Carol says, I'll need a couple hours to run some additional tests against the new host, because that's how Carol does things. Stand by. Oh, wait, let's go back a little. So this is great, right? Carol's a great employee, but what happens, I'm sorry, I have to stop for a minute because I need my notes. And I don't have them here. 1 second. How do I do this? One second, sorry. Okay. Carol's doing a great job, but all the work she's done isn't being properly leveraged by any other groups. Now Carol has to do extra work to validate the process. She's a service owner. Her productivity suffers. If it happens once, that's fine, but it can't happen with every migration. Carol can't waste 3 hours a month or 3 days a month on migrations. She has other work to do. She's a very valuable employee. And by the way, these are not individuals that I'm making fun of in any way. These are just more like attitudes or maybe even facets of an SRE's personality, because I know some days I feel like Gene. I try to be Carol, but some days I feel like Gene. Some days I feel like Angus. And then, of course, lady not appearing in this film, Karen, the employee who left the company, who took all the knowledge they didn't write down with them. That's never good, because they have a service they left behind and nobody knows now how to upgrade it. So a better way would be to automate everything. Automate your canary analysis. You have a software-defined repeatable process for validation of new code rather than just somebody looking at a graph. Accumulated knowledge remains in the system as code rather than staying in someone's head that might leave. It can be generalized. So if there are 10 Java services that are unowned, we know from the other 120 that are owned what the normal metrics to look at for those services are. So we don't necessarily need the information in Karen's head. And then optionally, we can provide manual go or no-go still, for Gene, because he's going to want that. Bad results, we update our model in source control. We don't have to just remember to do it differently next time. So here's how it works. Essentially, we have these components that we've used. Spinnaker and Kayenta are the main components. You could do everything. You could do canary analysis just with Spinnaker and Kayenta. You don't need all these other things, but just because of the way our systems are designed, there are a lot of different components that we need to touch. This is essentially the process flow. It starts in the top left with creating the canary and control clusters. We basically blow those away and start from scratch each time, just because we want a fresh install of both. We move to building one of each instances, 1 over n. N would be the number that we're planning to build. We do a service health check to make sure the service actually started up properly. We wait for a convergence period to have our metrics converge to whatever is normal for them. So obviously when you start a service, it's going to have higher CPU, disk, I/O, memory usage. But after, eventually it converges to a certain state. And then we run our canary analysis. And if the cluster is at the desired size, we stop there and we go to the manual go no-go decision. If it's not at the desired size, we build another host, repeat the process. Here's essentially the way the system looks. Oh, you can't really see the bottom of that, but it's just lines, so it's okay. The metric data gets pulled in from our OpenTSDB into Kayenta. When the webhook runs, the main component that we've written or that we've developed ourselves is the cycle.pex, which is a Python library wrapped into a PEX And that's all run by Jenkins. Cycle calls the webhook back to Kanta to grab the metric data and run the canary analysis after each run. And obviously everything touches the AWS API because we're all in AWS. Configuring Spinnaker is fairly easy. There's a lot of gotchas. It does take a while to get to sort of a good state. There are some bad things that can happen if you don't do things right. But I mean, nobody's going to die or anything. It's just, you might get an error. So you do have to set up a pipeline. It's kind of weird because you have to set up a pipeline and a canary config. You have to set up a pipeline to run the canary config. But there's a lot of different parameters that you can define. You can define how long you want to wait before doing the canary analysis, collecting data. We use 20 minutes. I think 30 is recommended. But we found that our metrics converge within 20, so we just use that because it saves time. You can delay a certain amount of time before starting the analysis. The interval thing, I don't really even know what that, oh, I'm sorry. The interval, you can define a separate interval for each canary analysis if you want, otherwise it will use the default in the lifetime. And then the step, I really don't know what that does because there's no help, and I think it's some sort of polling thing, like internal, but I'm not sure. You can configure scoring, so you can essentially define which metrics are more important and which are less important. You can also group your metrics into different groups, configure them that way. You can assign each group a weight, and then you can define what your scoring thresholds are, your marginal and pass. If it's below 50% for this one, it would fail. In the marginal, I believe it would keep going, but ask for marginal or pass would keep going, but ask for user confirmation, the manual no-go, no-go step. Configuring the pipeline, also fairly easy. You can tell it what to do if a stage fails. There are a bunch of different conditionals you can add. We didn't get too deep into those, but we may wind up using those in the future. For adding a metric, it's basically just defining which group it's in, giving it a name, deciding whether you're going to fail on an increase or decrease. For example, you might know that Ubuntu 18 has 2% worse CPU performance than Ubuntu 14, or at least we found that out a couple weeks ago when someone ran some tests. So you might say if CPU usage goes up by 4%, then we should fail because probably something else is wrong. But we're expecting that 2%. You can define what happens. The NAN strategy is what happens if it can't get a metric. And then scope name, OpenTSDB. I'm actually not an expert in a lot of this stuff. I never really put the time into figuring out how it works. So, but essentially that's our metric name. The aggregators and stuff are still sort of black magic to me. But oh, and you can't see the bottom of that. There's an aggregator and a downsample below that. So you can downsample 2 different time periods. And then you can, like I said, you can group up your metrics. This only has 1 group, but you could add a separate one, as many as you want. I don't know what the limit is, but you could add more than 1 for sure. And in each metric group, you can give a weight. So you can see down at the bottom there, this is pulled from a different pipeline, but we weighted system metrics and service framework metrics, both at 50%. Once the canary analysis is done, you'll get an output that looks something like this. The disk I/O, it is weird that it passed because it's such a huge difference, but the cluster I ran this on had like no disk I/O, so it was probably just like 1 file being read or something. I think because it was so low, it just passed it because it was below the threshold. And this is the kind of output you'll get. Essentially, it'll give you a graph of the metrics between the 2 different stages, the canary and the control. And you can look at those. It prepares a nice report for you to look at. You do want to size your clusters. 1 second. You want to size your clusters, canary control to similar sizes in order to have a good basis for comparison. You wouldn't want to have a canary of, say, 20 instances and a control of 1. That would expose you to some potential differences. Load balancers aren't perfect. I mean, they can balance traffic perfectly, but they don't necessarily know what calls are being made. You could make an expensive call to one server, and then it looks like the CPU is very high, and other servers could not be serving those expensive requests and look like they're very low. Typical, I think, a lot of people will use a 5% canary who just have a canary and don't have control. We're using 10 and 10. We think that's good. If you're using like 1%, it might be okay, but probably bad. And these aren't to scale. Oh, and the black is the prod. I don't know why it's cutting that off. The overall effort for this, it was planned to be a 6-month project for 2 to 3 full-time engineers. But of course, everyone knows no SRE can work full-time on one thing. There's always users to help, site issues to resolve, and shifting priorities. The actual effort turned out to be about a year to implement this fully. My colleague Ruth wrote about 700 lines of Python and about double that in tests because Ruth is very thorough. But that's mainly the logic of making web calls to webhooks and things like that. It's fairly simple. And you could really implement all of this in Python if you wanted to. We chose to use the Kanta and Spinnaker solution because it was fairly stable and mature, and it does all the things we needed it to. So we didn't see a need to develop anything ourselves for that. We did have to write our own OpenTSDB plugin for Kanta because it doesn't natively support OpenTSDB. It supports like 4 different metric systems, whatever they use at Netflix internally, and then a few other ones. It wasn't too difficult to modify because all the existing code was written for those plugins. So, and eventually we hope to contribute that code back to open source so that the open source community so that other people can use it. Future plans we have for this system, we'd like to integrate machine learning code to the canary process. So even the tweaking and the iteration can potentially be done by robots in the future or computers. We want direct integration to our build system. Currently, this is a separate system, only because our build system was sort of in a state of flux when it was created, and we couldn't integrate it directly at the time. And we want to add some additional tooling. It is a little bit tricky for service owners to have to configure things in Spinnaker, so we'd like to make that a little bit easier for them so they don't need to know all the technical details. So here's some additional resources. There are a lot of presentations that have been done on this already. I have the links in here, so hopefully they'll be available in the PDF that's going to go online, and you can copy and paste them instead of having to type them. And we are hiring, so come work with us. If you want to scan this, I don't know if you'll be able to, but if you can't, that's the email address. And that's pretty much it. Anybody have any questions?
I have 2 questions. The first one is related to the cluster sizing part. Does that mean your system actually do canary and the control and the check? No. It's the for the comparison, right? Mm-hmm. Between different tasks. Do you actually do multiple tasks across multiple data centers?
Well, we don't do tests across multiple data centers. We do the tests across the different clusters. So we compare the overall metrics of the canary cluster with the overall metrics of the control cluster.
Okay. Have you ever considered like doing it within the same cluster because they have very similar machines? Then you can compare within one cluster.
Well, they're really all one cluster. I mean, they're all running the same version of the application. It's just that they're running different versions of underlying software, such as runtime, operating system versions, and things like that.
So basically, my second question is at Google, we do canary analysis as well. And I was saying like lots of different ways it can feel. So I'm actually very curious, like, can you share like 1 or 2 examples, like how it didn't work that well? Yeah.
Yeah, actually, when I was finishing up the implementation there, we actually had a lot of issues with OpenTSDB. Our OpenTSDB cluster has had some growing pains recently, and there were some weird errors coming up. We had to patch some bugs in the Kanta plugin because there were some exceptions that were getting thrown, things like that. That was actually, I think, the largest issue we had. Next.
So application rolling out pipeline and the OS upgrade pipeline is the same, or you have different pipelines?
Currently, they're separate.
It's separate?
Yeah,
So
and-
you prepare the pipeline for each services?
Yes.
Okay, thank you.
Just wondering why you decided to use just the CPU, I/O, and memory versus monitoring, I guess, the request performance.
Oh yeah, that was just an example that I created for the demo. It's just to show it how it's done. We use a lot more metrics than that in our actual production analysis.
Hi, I'm just wondering about your false positive rate.
Mhm.
Can you share about like how you deal with it?
False positive, as in the canary analysis returns a success when it should have failed.
Or like false negative, like either way.
Well, we do have the manual step, so we can override the decision of canary at this point.
Yeah.
We've
Like overall, like how would it like introduce more like burden to the SRE? Like they have to manually override the exam every time.
Well, yeah, I mean it's a burden at the beginning, but hopefully over time you iterate and you
Sure.
you automate those things away. I mean that's the plan at least.
Thanks.
Any other questions? Okay, thanks a lot, everybody.